Hello everyone, welcome to my channel MP Academy. Today we are going to discuss about Cbse class 10 chapter 1, that is real numbers. Okay, so some concept we already know from class 9 about real numbers, and this is the second page of real number, that is in the class 10. So before to solve the exercise, first we have to know about two things, that is Euclid division lemma and Euclid division algorithm. So first I discuss about what is Euclid division lemma. So the statement is, given positive integer a and b, there exists unique integer q and r satisfying the relation a equal to bq plus r 0 less equal to r less than b, where a is greater than b. Okay, therefore a is greater than b, so we can write a equal to bq plus r, where if we divide a by b, then we get q is the quotient or r is the remainder. Then we can write a equal to bq plus r. This is the division algorithm that is already discussed in the class 9. Again, this is the statement of Euclid division lemma. So now we are trying to understand by taking an example. Suppose I want to divide number 7 by 2, then 2 divided by 7, then what is the quotient? It's 3. 2 3s are 6 and remainder is 1. So r equal to 1 and this is equal to q. So quotient equal to 3 and remainder equal to 1. So now 7 is greater than 2. So 7 can be written as 7 equal to bq, here b equal to 2. So here a equal to 7, b equal to 2, q equal to 3, r equal to 1. So according to division lemma, Euclid division lemma, we can write 7 equal to bq, that means 2 into 3 plus r, that is remainder, that is 1. So 7 equal to 2 into 3 plus 1. This is the Euclid division lemma, and this division lemmas we use to solve the exercise problem. Okay, and next is Euclid division algorithm. So what is Euclid division algorithm? This Euclid division algorithm we can use to find the HCF of two positive integer. Here to obtain, what is the statement? This is the statement, to obtain the HCF of two positive integers, say c and d. Okay, where c is greater than d. Okay, so we want to find the HCF of two positive integer c and d, where c must be greater than d. Follow the steps below. Step 1, apply Euclid division lemma to c and d to find the whole numbers q and r such that c equal to dq plus r, 0 less equal to r less than d. So first we have to apply Euclid division lemma that we already discussed. Okay, then step 2, if r equal to 0, if this r equal to 0, then we get the HCF. What is that HCF? The HCF is this d. If r equal to 0, then HCF of c and d is d. Okay, if r is not equal to 0, then again apply division lemma to d and r. If r equal to 0, then we get the HCF. If r not equal to 0, then again we have to apply the division lemma that we apply in step 1. Okay, and step 3, continue this process till the remainder r is 0. So we have to continue this process till the remainder will be 0. The divisor at this stage will be the required HCF. So when we get r equal to 0, that is remainder equal to 0, and on that stage the divisor is the HCF of that two given positive integer. Okay, for example, now we try to understand by taking an example. Suppose we have to find the HCF of 135 and 225. So first we use, according to step 1, first we use Euclid division lemma. So what was that statement? First we have to divide 135 by 225 because 225 is greater than 135. Then what we get? Q quotient equal to 1 and remainder equal to 90. So 225 can be written as B into Q, that is here B equal to 135, A equal to 225. So 225 is equal to 135 into 1 plus remainder R. So here R not equal to 0. So we have to go to the next step. Again we divide 30. We use division lemma, Euclid division lemma, among 135 and 90. Again divide 135 by 90, then quotient is again 1 and remainder is 45. So this can be written as 90 into 1 plus 45, again R not equal to 0. So again we have to apply division lemma, that is, so again 90 equal to, now if divide 90 by 45, then what we get? It's 2, it's 90 and it's 0. So R equal to 0, Q equal to 2. So 45 into 2 plus 0. So ultimately we get remainder equal to 0. Therefore HCF of 225 and 135 equal to its 45 according to Euclid division algorithm. When the remainder is 0, the divisor at this stage will be the required HCF. So at this stage, in which stage? When the remainder is 0. So in this stage remainder will be 0. So the divisor, what was the divisor? It's 45. So 45 is the HCF of 225 and 135. Okay, now we solve the exercise problem of chapter 1, real numbers. Now first question is, use Euclid's division algorithm, find the HCF of question number 1 is 135 and 225, and second is 196, 38,220, and third is 867. Is already solved. I solved in the previously. Now we solve the question number 2. So what was the division algorithm of Euclid's? That is, first we have to identify which number is greater. Here see which number is greater. Here 38,220. 38,220 is the greater number, and then 196. So first we divide 38,220 by 196, and then what is the quotient? Quotient is equal to 195 and remainder is equal to 0. Okay, remainder is equal to 0. So we can write 38,220 is equal to 196 into 195 plus 0. A equal to BQ plus R. Here A equal to 38,220 and B equal to 196. Okay, since R equal to 0, so this process I stop here, and we get already HCF. Divisor is the HCF, so which is the divisor? 196 is the HCF. Next question is, we have to find the HCF of 867 and 255. Now 867 is greater than 255. So here we apply division lemma according to the division algorithm of Euclid's. So here we divide 867 by 255 and get quotient equal to 3 and remainder equal to 102. So we can write 867 equal to 255 into 3 plus 102. Now 102 is not equal to 0. So now we have to again apply Euclid's division lemma. Now we divide 255 by 102. Now then we get the quotient 2 and remainder equal to 51. Okay, now 51 is again not equal to 0. 51 is again not equal to 0, so we have to again apply Euclid's division lemma. Again we apply Euclid division lemma. Now we divide 102 by 51, then quotient equal to 2 and remainder equal to 0. Remainder equal to 0, so 102 equal to 51 into 2 plus 0. Now remainder is 0, so I stop this process, and ACF of 867 and 255 equal to 51. Now next question number 2. So that any odd integer is of the form 6q plus 1, 6q plus 3, or 6q plus 5, where q is an integer. See here, every first digit is 6, right? So here b equal to 6, and let a be any positive integer and b equal to 6, because all the first digit is 6. 6q plus 1, 6q plus 3, 6q 5 plus 5. That's why I take b equal to 6 and a be any positive integer. Now Euclid's algorithm, a equal to 6q plus r, and r is between 0 and 6. 0 less equal to r, less equal to 6. Therefore if we put consecutively 0, 1, 2, 3, 4, 5, then we get a equal to 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, and 6q plus 5. Now 6q plus 1 can be written as 2 into 3q plus 1. Now if we put 3k equal to 2k1, then is equal to 2k plus 1. 6q plus 5 is again in the form 2k3 plus 1. Okay, if we put 3q plus 1, this is equal to k2, then and 3q plus 2 equal to k3, then each number is of the form 2k plus 1, or 6. Therefore 6q plus 1, 6q plus 3, 6q plus 5, every number is of the form 2k plus 1, where k is an integer. Therefore 6q plus 1, 6q plus 3 and are not exactly divisible by 2, so these are odd numbers. So we can say that any odd integer can be expressed in the form 6q plus 1, 6q plus 3, or 6q plus 5. Next question number 3. See question number 3. Now we have to the two groups are the merged same numbers of column. What is the maximum number of column in which they can merge? So here in this way we arrange. Now in front one band army member stand, and beside him the members of army congregant are stand. In this way they stand, and total number of congregant is equal to members 616 and army band member 32. Now we have to find the ACF. The ACF 616 and 32 will give the maximum number of columns in which they can merge. We can use Euclid's algorithm to find the ACF that we already discussed. So first we divide 616 by 32, then we get quotient equal to 19 and remainder equal to 8. So 616 can be written as 32 into 19 plus 8, equal to bq plus r in this form. Now 8 remainder equal to 8, this is not equal to 0, so we again apply Euclid lemma. So we divide 32 by 8, then we get quotient equal to 4 and remainder equal to 0. So ultimately we get remainder equal to 0. Therefore ACF of 616 and 32 is 8. Therefore they can merge in 8 column each. It's completed. Next question number 4. Use Euclid division lemma to show that the square of any positive integer is either in the form 3m or 3m plus 1 for some integer m. So here first number is 3. Each number, see the number form the number is in the form 3m or 3m plus 1. So first digit is here 3, so we get b equal to 3. Let a be any positive integer and b equal to 3. In the previous question we take b equal to 6. Again, using division lemma, Euclid's division lemma, we can write a equal to 3 cube plus r for some integer r, or 0 less equal to or less than 3. Therefore a is of the form 3q plus 1, 3q plus 2, by putting r equal to 0, 1, 2. Okay, now square of the numbers, so a square equal to 3q the whole square, 3q plus 1 the whole square, 3q plus 2 the whole square. Now to calculate 3q plus 1 whole square, we have to use the a plus b whole square formula. That is the formula is a square plus 2ab plus b square. Okay, so first number can be written as 3 into 3q square, and second number can be written as 3 into 3q square plus 2q plus 1, and third number can be written as 3 into 3q square plus 4q plus 1 plus 1. I just simplify by using that whole square formula, and then if we put 3q square equal to k1, 3q square plus 2q equal to k2, and 3q square plus 4q plus 1 equal to k3, then ultimately the square is in the form 3k1. If we put 3q square equal to k1, 3q square plus 2q equal to k2, and 3q square plus 4q plus 1 equal to k3, then ultimately we get 3k plus 1, 3k3 plus 1, where k1, k2, k3 are positive integers. Hence it can be said that square of any positive integer either in the form 3m or 3m plus 1. Next, question number 5. Use Euclid division lemma to show that cube of any positive integer is of the form 9m, 9m plus 1, 9m plus 8. Here the form are 9m, 9m plus 1, 9m plus 8, but I not take b equal to 9 because the cube of, that's why here see first digit is 9, but here we take b equal to 3 because cube, let a be any positive integer, b equal to 3, where a equal to 3q plus r, q not equal to 0, 0 less equal to or less than 3. This is the Euclid's division lemma. Now case 1, if a equal to 3q, then aq equal to 3q the whole cube, this is equal to 27q to the power q, 9 into 3q equal to 9m, where m we take 3q, q to the power q. Okay, so aq is on the form, that is first number is of the form 9m. Again similarly, if we get the second one, then we get, and simply after simplification we get aq equal to 9m plus 1. If a equal to 3q plus 2, again by simplification we get aq equal to 9m plus 8. Okay, so we can say that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8.